Bismillahirrahmanirrahim. Welcome to Easy Learn, and this is the episode 16, and we are going to just start another important episode that is relevant to the previous episode. But uh, before going to start, I just want to tell you here that our chapter number 1 of the network analysis is going to just wrap up. Then we are going to move toward the next step of the networking. After this is chapter number 1 is actually the introduction of the network analysis, but it is really important. The previous episode is the most important episode of the chapter number 1, and I think you need to watch it again and again. And if you memorize this episode, the previous episode, and that is the 15th episode, then the whole chapter number 1 will be I think don't need to be further study, because episode 15 is the major and the final results of the all other episodes. Then first of all, I also want to tell you about that our main book that I'm following right now is Network Analysis, third edition by Van Wackerberg. You can also consult other books, because I am not consulting only single book, and I also recommend others because this method is mostly appreciated and mostly preferable to follow more books than one. So mostly I am following this. Our major route is mostly following book is actually Networking Analysis by Van Wackerberg, but you can also consult other books for your own purposes. So the chapter number 1 of this book that I am following is going to be complete, and I'm going to start the next chapter from the next episode. So at the end of the today's episode, I'm also going to provide you some stuff that on our Facebook page you can go and watch these that are some practical questions. Try to solve these questions, because and some further reading and the digital computer exercises or some other stuff that you need to read by your own, because I can't read all the things of the books here. Some really important things you need to read by yourself, theory type. So before further discussion, let's first discuss the units of the some quantities, some parameters that we already discussed in the chapter number 1, and that will be used in the coming episodes. But first let's discuss them with the help of some units. Okay, here is the picture of the units and scaling. This is very beautiful picture because very easy to understand. Number 1 is the quantity charge, and it is represented by small q, and the unit is coulomb, named on the scientist, and no equivalent units here. So we can also represent abbreviate it with capital C to represent the charge. Second quantity here is the current. There are the two symbols, smaller I and the capital I. First, let's discuss the two symbols scenario. Those quantities which have the two symbols are here: current, energy, voltage, power. Why there are the two letters to represent these quantities, smaller and the capital one? Let's just consider the story of this, like current first. For example, current or voltage. These are the quantities. Let's discuss this current. This is a current that is just varying with the passage of the time. Here the time is increasing. When the time is increasing, the quantity is continuously changing. For example, this is a sinusoidal wave, and with the passage of the time, this current increases to the peak, and let's suppose it is 10 volts here, and then negative side also 10 volts. This is positive 10 volts and the negative 10 volts. This sinusoidal it means that it is continuously varying. For example, at this point, if we are taking here, it is, let's suppose, 3 volts. If it is, sorry, it's a current graph, it's a current graph, 10 amperes here, 10 amperes, because we are considering current, not voltage. 3 ampere. For example, here if we take the reading at different seconds, 1 second, at 2 second, it is maybe 7. let's suppose. And when if we take the reading here at different time frame, let's suppose at 4 seconds, then we can say it is maximum, and let's say it is 10 ampere. So what does I want to quote here and want to tell you here is actually with the passage of the time the quantity is varying. When the time varying quantity is discussed, then there is a smaller representation of the letter is used, like a smaller I for the current, small w for the energy, and V as voltage and respectively. Then there is a capital representation that is used to represent the time invariant quantity. Here you can also see the details of this discussion, such as the average means that the quantity, let's suppose I'm considering and I'm saying that here we using a filter, here we using the regulator that changes this voltage into a fixed voltage, like suppose that DC voltage. It is a time invariant. If it is a time invariant and it is a constant level, let's suppose it is constant level, then we will take it as a capital I or a capital V for the current and the voltage respectively. And this is the story of the two symbols here. Okay, let's continue this. The current is represented with the ampere, and the coulomb per second is the equivalent units. Coulomb per second is also taken as the ampere. So AMP is the short form for the abbreviation. Flux linkage is the psi. It is the Weber turn and no equivalent units. It is WB, named on the scientist Weber. And flux linkages is a very important term in the networking. We already discussed it, because these already all terms are actually already discussed, but this term is very important, and I just want from you to keep it in your mind and differentiate the flux or the flux linkages, so that we will not mess up in the coming episodes, because the next episode are really a bit tougher, and we are going to take one step towards the networking. We're going to move and took one step actually. Okay, energy, W is used to represent the energy here, and the joule is actually the unit. Voltage is represented with volts. You are already familiar with power with watts, capacitance with farad, inductance with the Henry. This is named on the scientist, and you can see here the two symbols L and N. If you remember, I told you when I was teaching you about the inductance, the two inductance actually is the like this. It is a magnetically coupling of the coil. When the current is flowing actually like this one, suppose the current, this is I current entering into the coil, it may have the flux that is produced, flux linkages, and the flux linkage can be seen in the coil itself. That is called the L, means the self inductance. The effect is observed in the same coil. But if there is another coil, two coils are actually used, then the behavior of the other coil that is attached with the flux of the first coil, this is the first coil, this is the second coil, then we will call it as a flux linkages. Okay, so the flux then we will call it as a mutual inductance. Mutual means two, the involvement of the two or more. So this is the unit is the same. Weber per ampere is the equivalent unit, and H is the representation, capital H. And here we go, the representation of the resistance and the conductance of the symbol is actually the inverted form. R and G are the different representations, and if you don't these are the reciprocal terms. And there, if you notice here, here we have lack and the missing one term is missing here that we discussed, and that is also the reciprocal of someone. If you remember, that is the reciprocal of actually capacitance. If you have your mind, we discussed previously when we discussed the capacitance, I think maybe in episode 5 or 6, I don't know right exactly, we discussed there the inverse and the reciprocal of the capacitance called the elastance, represented with the D. So that's missing here actually. Anyway, resistance and the conductance are the opposite terms, and the volt per ampere or the ampere per volt, you can see here volt per ampere and the ampere per volt. So don't mess these two terms, don't be confused in these two terms. Resistance, just usually this term is very important. Resistance is represented with capital R, and remember this term, this one, then you will easily catch this term. Time is represented with a T, frequency with F, and there are the two representation of the frequency, that is a simple frequency, that is F, and that is another frequency, we call it actually angular frequency, and the representation of the symbol is different. Omega is used, and omega is equals to 2 pi F, and the unit abbreviation is none, but this simple frequency is represented with the hertz. Okay, so these are another scaling that is very important, because in engineering applications other units which are multiple or the sub-multiple of these units will be used by employing the prefixes as shown in the figure. You can see here that different 10 raised to the power, different multiples of the 10 in the, like this is a 10 raised to the power 2, multiples of the 10 are seen, and this is called prefixes. Most important prefixes, you just don't need to look at this this matrix, just need to look at the first this one actually. Even you don't need to pay more attention to the symbols, but I recommend you to memorize it. At least memorize here to at least memorize to 10 raised to the power 6. At least this table you need to be in your mind at fingertips. Mega 10 raised to the power 6, kilo 10 raised to the power 3, and remember that mega is represented with a capital M, and here only one Greek letter you can see, that is the micro 10 raised to the power minus 6. So this is what you can easily memorize by yourself. I don't need to discuss it here right now. Okay, so here we can see the physical system as a circuit. What does it means? It actually means that we already discussed the three electrical phenomena experimentally in the previous discussion, previous episodes. What are the previously discussed three basically systems? That is the capacitive system. A system can be inductive, a system can be resistive. There are the three different types of the system that we discussed. But how we can use these system in our daily life, how we can apply the formulas that we derived, this is going to be discussed actually in the chapter number 2, but just for the sake of the touch and just for discussion of the physical system. Physical system means, for example, a motor is our physical system. You can easily see it, but how we can draw the motor's equivalent circuit on your notebook for the networking analysis. Actually this is a matter of the discussion, and we need to consider the details about it, we need to study about it. And one thing you need to keep in your mind, the more and the more you do the practice, it is a key for the success in the networking analysis. Like for example, a phenomena observed experimentally can be described in terms of the circuit phenomena, circuit parameters. A problem that we must eventually face in making use of the circuit concept is that of representing a physical system in terms of those parameters like we derived in the capacitive or the inductive systems. Like for example, let's say we have a case here, representation of the electrical motor or the piezoelectric crystal. Let me tell you first about the piezoelectric crystal. It is a type of the crystal like this one. When we check the voltage here, the voltmeter shows zero deflection, means no voltage can be experienced in this piece of the conductor. But as we squeeze and apply the pressure on this material, it provides some little bit voltage can be seen, some voltage can be produced, opposite charge appears here on the surface, opposite surface, and due to this we have seen of deflection on the voltmeter. This is called a piezoelectric crystal that produces a voltage when pressure is applied on it, or a coil of the wire. Third one is a coil of the wire. So these are the different type of the actually circuits, how we can use these integrated circuits in our equivalent circuits. Suppose we examine some arbitrary physical system, looking for portions of the system to be replaced by equivalent parameter. Possibly the resistive effect would not possibly the resistive effects would be most easily recognized. Remember that resistive phenomena is most easiest process to draw and recognize, because resistance actually we use here is a linear resistance. There are the two types of the resistance. That means, for example, I say that the wire of the resistance is, for example, 5 ohm. It means that it is linear. For example, we double the length, it means it is now 10 ohm, and the resistance is not varied and it is a constant throughout the process, and with the passage of the time it is constant, or with the temperature changing it is constant. These are the different parameters what I can change, but still the resistance is constant. So this type of the resistance will be discussed for the better understanding. Keep in your mind that resistance changes in actual conditions. Resistance changes, many factors are there that change its value. It is not actually the linear graph, its graph is changing continuously. But we are discussing in our networking for better understanding at the starting episode usually, resistive or the capacitive or inductance, a linear graphs there, not a non-linear circuits. A part of this system made of the material of high resistivity. Any system that is made up of the high resistivity with a very small cross-sectional area and the appreciable length would be recognized as the equivalent to large resistance, and could easily be distinguished from another part of the system of small resistance. This is what I am reading from the book of the networking analysis, that is telling me about the resistive circuit, that how we can use and how we can draw the resistive circuit. For example, there is a large conductor of length L, and it has a particular resistance, and we can draw it in a circuit with this symbol that is used to represent the resistance. And same is the case and different approximations. By the way, that in the previous slide, this equivalent circuit or a model is actually taken of the excited antenna circuit. So, and this diagram is taken from the piezoelectric resistor that we was discussing in the previous slide. What are about the piezoelectric circuits? Okay, there is a capacity. First let's discuss capacitive. Okay, let's first discuss the capacitive effect between any two parts of the system exists if the two parts constitute a system capable of concentration of the charge, producing a high electric field. Let's suppose, say, large area of the charge stored and small distance from part to part. They are close enough, and the distance is very small. And then if the current is coming out from the both sides and the distance is very small, then their area is large enough to produce some to store some charge on their plates. Then this is called a capacitive system, can be seen there. The capacitance of that portion of the system is large, and the inductive system is associated with every current carrying conductor, and an effect of the mutual inductance between every pair of the conductors, at least one of the which must be carrying current. We have a inductive system. This can be represented with the this type of the symbol, like this symbol, that is this solenoid type. I'm not able to draw here actually, that is why I'm using the diagrams here. If I was able, then why I'm using the diagrams. An inductive system, there are the two types. It may be a self-inductance or the mutual inductance. Self-inductance means the inductance phenomena can be observed in the same coil that was producing, as I was discussing in the previous slides. Then we were going to discuss it self inductance as L, while other is mutual inductance with the M. So the inductance, if there is a mutual inductance, then the first coil or the second coil, if there are two coils, then one of them must be connected with the current, so the other coil can receive the flux linkages from the first coil or the second coil. Means one coil must be connected to the current so that the flux must be produced and the other linked with it. So the much large so much for large effects. What about the smaller or the secondary effects that can be recognized in much the same manner? Just how many effects must be taken into account in representing a system by the equivalent parameters? These are the different questions actually coming in the mind when going to draw and going to solve our arithmeticals. But the best answer to them is to the accuracy of the result will depends on how much separate electrical effects we can take into account by a parameter. Mean our practice, all the answer is our approximations. Approximation require engineering judgments, and the approximation engineering judgment approximation is an approximation which is valid in one case and it is not valid in all the cases. Means that for this system we can consider a special approximation. For the other system we will discuss a different approximation. That is not true for all the scenes, but for the understanding we use this. So these are the different schemes. Approximations requires judgment, and that comes from the experience. In this discussion to follow in other chapters, we will assume that when a schematics of a system is given, all significant parameters have to be taken into account. Engineering judgment has been exercised by the individual who made up the problem, but when the situation finally applies the technique of analysis to the problem, then he makes up the question associated with the approximation must be answered. It is difficult to write answers to such questions in textbooks experimentally in using the best teacher. So this is what I was reading again from the networking analysis by Van Wackerberg book. Actually this book is here at the ending of the first chapter. The lot of the theory theory pages are attached in the chapter number 1 ending section. So I was just reading some portion of this, that if in case if you are not able to join us on our Facebook page, you can that I can read some portion of this. And in this whole scenario the author just want to tell you about the judgment. Engineering judgment means the approximation for one circuit that you are going to choose according to the desire and according to the situations. You are considered to be expert if you have enough capabilities to write the structures of according to the desire. So we assumes that variation in the magnitude of the charge, current and voltage according to the desire. Here you can see that a system, this is a network, and here this is a non-linear system we are seeing here. This behavior is non-linear because you can see with the passage of the time the current is increasing, and then after some time this is going to be non-linear. It is going to be changed its position, its direction. It may be linear if it is going in this direction like this, but it is going to be non-linear if it is changing its position according to this. If it is going to downward, either upward, maybe it toward any side, but this is going to be non-linear for any device. We're just considering. But in networking analysis, to make it simpler for understanding, we are going to replace it with a linear resistance, and the linear resistance is represented with this type, and this is the actually approximation circuit, and this is called linear judgment, and it comes from the experience. And if we have more experience, then and of course we can easily able to apply our knowledge. A system composed of such elements is said to be linear, that we already discussed, while we will assume that all the system to be considered, unless otherwise we will specify in our discussion, are linear. We therefore exclude nonlinear elements from the networking analysis of our series. So two such systems are illustrated by the characteristics A and B diagrams. You can see in front of you there are the two diagrams. Number one is the inductive system. This one diagram is the inductive, and there is a second diagram, number two, that is the capacitive system. And this loop is actually a hysteresis loop. That is the non-linearity. Clearly can be seen that if you are going to increase the current, the flux linkages is increasing in this way, but when going to the back side, it is not going to touch your 0 point, but some flux is stored, and it is going to be here, and this is the fourth and the fifth. This is actually the very beautiful graph, and the whole episode is required to explain it. I will explain it later on when it is the right time to explain. But right now, this is from here, this can be seen that if it was a linear, then what happened? Then if it is a linear, then this is the first step, and in the second step it needs to become on the same position, the same track, then we will call it as a linear. But right now this is a purely non-linear, and here you can see this is a non-linear portion of the capacitive network as well. So both has a non-linear relationship between Q and V. Some non-linear system can be represented as a linear under certain conditions. Transistors are also non-linear, but for certain analysis may be considered linear over a restricted range of the operations. That depends upon us. So here some approximations, as we are discussing, it is important to understand that the model of the system is not unique, that the model actually used will always depend. Like this, for example, if we have a physical system, there are the number, an unlimited number of the models we can derive from this. What does it means? It means that depends upon the accuracy. For example, if we need a high accuracy, we can use another, we can use this system, we can use this system, we can use this system for another accuracy. So physical system or a device or a system, there may be many possible models, and a choice of these available must be made before analysis. And according to this suggests that the given physical device or a physical system can be represented by many different models. Okay, so I think that is the enough. But before going to wrap up and going to stop the recording, I just want to tell you that the further reading and some of the symbols for the NP and BNP bipolar transistor and the successive more complicated model for the bipolar transistor, I will just add in on our Facebook page, and the digital computer exercises for you, and for further reading stuff and some other charts I will upload on the Facebook page. Further discussion inshallah will be continued from the next chapter, that is going to start from the episode number 17 inshallah. And at the end, I just want to tell you about the name of the second chapter, that is the conventions for the describing networks. So inshallah, stay tuned with us and enjoy the better taste of the networking. So Allah Hafiz.